La profesora, bueno, tenemos el placer de tener a la profesora Diane Cook. Ella es de Iowa State University, es profesora titular de full professor. La profesora Cook tuvo su grado de doctorado en Rutgers University. Es fellow de la Sociedad Estadística Americana. Es una líder en un área de visualización, análisis exploratorio de datos. Tiene más de 40 artículos de investigación en journals de alta calidad. Tiene un libro de Springer junto con Deborah Swain. Es la desarrolladora de bastantes paquetes de R para el análisis de datos y del software GBobby. Entonces es una muy buena experiencia, o va a ser una buena experiencia para nosotros como en la comunidad estadística de estar expuestos a la doctora Cook. Thanks for coming here to Mexico. We are very pleased to have you here, to be exposed as a statisticians to your expertise in the area of visualization. I told them your basic.
I think I got a lot of it. I think so. Yeah, thank you for having me come. It's a pleasure to be here. So,
just if you need a break, just.
Okay. So are we scheduled for? No, we've got 2 hours. So we'll have a break about halfway through.
Okay.
Yeah. Okay, and material. Just a little bit more on the background. So apologies for English. My Spanish is terrible. So I'm originally Australian too, and so my accent is a little bit different. If you please stop me and ask me to repeat something if you need me to say something again. I also work in various applications, so I have done some methods development a bit, but I'm currently working in bioinformatics with high throughput sequencing data. I'm also working with climate data. I just gave a workshop at the National Climate and Atmospheric Research Center in Colorado over the summer too. I'd like to start, if you wouldn't mind, if you would introduce yourselves to me and tell me just a couple of sentences about what you work on, because that will help me sort of digest all of your interests. So maybe we start on this side, if you want to know.
Actually, I'm teaching multivariate data
cool.
analysis in a postgraduate program at the National University of Mexico. So I came here to learn how to teach.
I should talk to you about some things too. Yeah. Okay.
No sé hablar inglés.
Okay.
Pero trabajo aquí en el INEGI y estoy haciendo una maestría en estadística.
Okay.
I am teaching on Benemérita Universidad Autónoma de Puebla.
Okay.
Interesting this then.
In time series? Okay.
I work at CIMAT in Guanajuato.
Okay.
I'm interested in string value theories, time series, and Gaussian processes.
So some physics?
Yeah.
Okay.
Atmospheric phenomena like rain.
Okay.
And also waves, oceanographic applications.
Okay.
I work here at CIMAT in Aguascalientes, and I'm very interested in general in multivariate methods, mainly in some called analytics. This is one of the most important.
Okay.
I'm a researcher in National Institute of Pediatrics in Mexico City, and my work is to support investigator data in the aspect of statistics and methodological issues.
Good morning. I teach, I'm a teacher. I teach statistics in the University of Puebla, UPAEP, and I'm interested in time series and theoretical.
Okay.
Good morning. My name is Juan Pablo. I'm also teaching at UPAEP, and I am interested in time series and analysis of data.
Mm-hmm. Okay.
Good morning, my name is Jesus Hinojos. I am a full-time professor at the University of Chicago in Juarez. And I'm teaching the research methodology. I'm very interested in this.
Okay.
Ricardo Rivera, INEGI, Aguascalientes. Trabajo en revisión de datos geográficos.
Okay.
Rogelio Ramos from CIMAT, work on applied statistics.
Paul Carrasco from INEGI. I'm working in statistics process development area here.
Mm-hmm.
My name is Enrique, I'm from la Universidad Veracruzana. Estoy igual specialization in statistics method.
Okay. Start the back.
Martin Aguilar Collins, mechanical engineering student from Universidad Autónoma de California, and I love math and statistics.
Mm-hmm.
Martin Aguilar, I'm a Lean Six Sigma Master Black Belt. I'm part of a consultant team, and also I'm an instructor and teacher in Celtic University in Baja California.
Mm-hmm.
And the reason why I'm here is that we normally use statistics for everything in the Lean Six Sigma methodology.
Mm-hmm.
José Rivera, I'm here in the Aguascalientes. I'm working on statistics method, particularly multivariate analysis.
Applied to what? So statistics applied to just applications generally. Okay. Mm-hmm.
Good morning.
Morning.
Javier Diane. I'm working here in Aguascalientes, and I'm working in analysis of multivariate data, statistics of statistics.
Okay.
Hi, good morning. My name is Humberto. I'm a student of statistical analysis master. Interest areas analysis in theory.
Okay.
Daniela Licea, I work for Sura Mexico, which is a pension fund and control fund administrator. I'm interested in whatever will help me improve the methods we use, especially for risk application.
Mm-hmm. Okay.
I am Gabriela Loredo. I'm a consultant data mining for a bank for BBVA and Comer. And I'm interested in all things about
Okay.
My name is Felipe. I am a teacher of math in the University of Guadalajara. We work in Mexico. My interest is in application of statistics, and in particular math modeling of environmental studies.
Mm-hmm. Okay.
Mónica Pérez from Instituto Nacional para Evaluación de la Educación, Statistics Applied to Evaluation.
Okay.
Mónica Figueroa, I'm a researcher in the biological area. I'm interested in the application of statistics of inferring phylogenies and phylogeography and conservation genetics.
Juan Fernández, estudiante de maestría de la Universidad Central.
Okay, yes.
I am Israel. I am studying probability and statistics in CIMAT, and I am interested in time series.
Mm-hmm. Okay.
I am Carolina. I am a PhD student from CIMAT.
Mm-hmm.
I'm interested in time series, multivariate analysis, and inference for processes.
Mm-hmm.
Good morning, Roberto Bárcenas. I'm studying a Master of Probability and Statistics at CIMAT.
Mm-hmm.
Good morning, my name is Julian. I'm a student from
from the Universidad Nacional Autónoma de Mexico. I try to do my thesis in manipulation data.
We need an extra chair. There's one extra chair here. We need an extra chair, right? Okay. How many of you use R? Okay. So about half. I'm going to primarily be talking about tools that you can use with R. Yeah. Anyway, we'll get started. So basically, we're going to be talking about multivariate data visualization, and this is a breakdown for the 3 days. So today I'm going to discuss some methods primarily. So we're going to spend a lot of time on methods, and we'll have some fun at the end to talk about classifying chocolates. And then tomorrow we'll start with missing data, ways of understanding missing data patterns, and assessing the imputation that you might do. And then cluster analysis. So clustering music clips. These is my records. And I also have some data on Mexico City climate and health variables. And then on Friday we'll talk about exploring longitudinal data. It's not time series data, which seems to be a lot of the expertise in here is on time series, but so it's quite different, but it's still temporal data and has some pretty unique challenges. And then the last topic will be on inferring significance. I know from a statistics perspective, we want to be able to say that what we find in this data relates to a larger population. And people think of graphics as not being inferential, but it can be. And so this will describe how you might be able to take what you learn from graphics and infer what it means for the larger setting as well. So some new techniques. So do feel free to interrupt me at any time to ask questions. It's much more fun for me to be having some interaction with you guys. So this is one of the data sets. So these first few slides are some of the data sets that we will work with. These are samples of milk and dark chocolates from around the world, and a few of the names. Unfortunately, I don't have any Mexican chocolate. I have some Colombian chocolates, as well as a lot of European ones and American. Primarily, we're looking at the difference between the milk and the dark in terms of nutritional measurements. Music clips. So I have some data that I collected from my own CDs. Some of you might relate to some of my music. You know, I have some ABBA from, way, way back, and some Beatles. Well, I was a little bit younger than the Beatles. Anybody know the Eels? It's a contemporary US band. They're kind of a little bit like the Beatles, really. And then some classical music and some new wave. This is Enya, very melodic music. So we'll take a look at so this is in the sense of, this data was audio tracks, and so they are sort of time series, but it's the summaries that I did of those audio clips. I didn't use the raw data. I did use the raw data, but I summarized the raw data with some simple statistics in order to understand, to be able to understand what the differences are between the different types of music. So we'll be looking at classical versus rock versus new wave, but generally seeing how those different songs relate to each other with clustering. Mexico City data. This is data from the full year of 2008, and we have measurements on deaths, different weather measurements, and the pollution every day, so daily measurements. And the primary question was whether the pollution contributes to mortality in Mexico City. It's data pulled together by Hadley Wickham, who some of you might know from using the ggplot2 package. So. And then we'll look at wages data. This is the longitudinal data. So we've got hourly wages of high school dropouts, which is part of a larger study, an ongoing study in the United States called the Longitudinal Survey of Youth. So periodically they survey the same cohort of boys that they started collecting back in the early 1980s, I think. And the primary question with this data is whether your wages increase the longer you're in the workforce. And so it's what you might expect to see is that wages do increase. The longer you work, you get better wages. So that's what we'll be studying with that data. And then the last one for you graduate students here, we have every so often, there are ranking systems that come out of the United States graduate programs. And this was the latest one produced by the National Research Council in 2010. So they ranked all of the statistics graduate programs in the United States. Actually, they did every different area, not just statistics, but the data that I'm working with is just the statistics programs. And they have two ranking schemes, an S rank and an R rank. And then they have a lot of different variables that are measured on each of the programs. So each of the programs needs to report these details to them, like the number of students, the number of faculty, how many women on the faculty, how many students graduate with a PhD, how long it takes them to graduate, the number of publications or average number of publications of faculty citations, GRE scores of students. There's like 30 or so variables that are used to come up with the rankings. So, you know, what is the difference between the different schools is really what we'd be looking at here. Okay, so those are the data examples that we'll be working with in different parts of the 3 days. These are the methods. So I am focusing primarily on the graphics. So we'll be primarily using these 3 methods for plotting data: scatter plot matrix, parallel coordinate plot, tours, grand, guided and manual tours. This is really where my research was when I was a graduate student, and I've worked on that some more since then. So we'll be talking about definitions, computation, and how you interpret them. Okay. So scatter plot matrix. Some of you, I feel like you'll know some of these methods, but I'll run through the definitions, make sure that everybody's aware of them. So scatter plot matrix, what you do is plot all pairs of variables. And so here I've just got a cartoon of 3 variables, and we have down the diagonal some view of the univariate information, so what's in a single variable. And then in the off diagonals, these are the pairwise plots, so V1 versus V2, V1 versus V3, V2 versus V3, and then that's the same in the top half, right? So it's a square matrix matching up the correlation matrix. And essentially what you're looking at here is whether you can use correlation as a summary of your data. So correlation is a good summary if your data is very sort of normal or regular. But if there are other aspects of your data, then correlation's not the right summary. And this can help you digest whether that's a good summary statistic. So here's an example with some of the Mexico City data. So we have 5 variables here. This is the deaths. Yeah, I'll put this on. So we have the health data, and then temperature, the average temperature, wind, nitrous NO and NOx. Now I'm finding the 2 of those is not sure about. Okay, this scatter plot matrix was produced with the ggpairs function in the ggalley package. This is a package that sits on top of ggplot2 and adds some more complex graphics to what you can do with the ggplot2 package. There's two main functions that we'll use in that package, ggpairs and ggparallel for the scatterplot matrix and the parallel coordinate plot. All right, what do we see? So these are the scatter plots here. In the top right off diagonal, we've got the correlations. So that's a common thing to do, is to show the correlation on one half of the scatterplot matrix, or to show some other representation. And so if you're using the ggalley package, you could show correlation, or we could show like a density plot or a linear model, or some other type of display up there, or just the same data again. So what we see with these scatter plots, so there's strong correlation between the two nitrogen measurements. It's a little bit rectangular, but otherwise it's fairly weak associations between them. There's not a lot more. There's no major outliers. There's a couple of points here that may be a little bit suspicious of being extreme, but they're not really far away from all the rest. This relationship is a little bit strange. There's negative association, but then there's a string of points here. This variable has something funny in terms of a lot of values on the same value. Maybe that was a non-detect. So maybe those were days when this wasn't detected. It was below the detection limits. And we'll see. Okay, so basically we're looking for pairwise association when you're making a scatterplot matrix. This is the same data using the package Yale Toolkit. This is a good one to know about as well. And they have a function called gpairs in it. And gpairs looks a little more like a base graphic. It's still built on the same structure as ggplot2. It's all built on Paul Morell's grid package, which is in the basic part of R. And the default gpairs plot will put a histogram down the diagonal and reflect, so the top half is the same as the bottom half. They're both scatter plots. It's just the order of the axes is reversed. So what we'd learn differently about this, depth seems to be reasonably symmetric. The mean temperature is reasonably symmetric. It's got a few low values. Depth, there's a few high values, a little bit slightly right skewed. Wind is fairly symmetric with a few high values. Nitrous oxide, it's a little bit multimodal, but maybe slightly skewed to the right, and this one also slightly skewed to the right. So they're not quite regular distributions. If we're modeling them, we may need to do some transformation on if we want to fit a nice model to them. One other key piece, I know a lot of you work with not just real valued data. Scatterplot matrices were originally designed for real valued, so numeric data. Both of these functions accommodate other types of variables. So if you have a categorical variable, you might do side-by-side box plots. And so you can do the scatterplot matrix with different plot types in here to handle different data types. That's pretty handy. So it's good to know about. Alrighty, parallel coordinate plot. How many people have heard of a parallel coordinate plot before? Okay. Teaching multivariate, you have to know that, right? Okay, if it's a first coordinate plot, it'll be very strange. It'll feel very strange because we're orthogonal axes. We're so used to axes that are 90 degrees from each other. Parallel coordinates flips that. So this is a conventional. I've got two axes, one for variable 1 and one for variable 2, that are orthogonal to each other. Parallel coordinates, those two axes are parallel to each other. So axis 1 and axis 2. Right. And then in terms of just two variables, there's a quick interchange between the two. If you have 3 points that are collinear in Cartesian coordinates, you'll have 3 lines that are parallel in parallel coordinates. Right? So strong collinearity or strong correlation matches flat lines in the parallel coordinate plot. And slightly different example, you've got the Cartesian coordinates, you've got 3 points that are collinear but in a negative association. In the parallel coordinates, they'll be all connected, crossing at a single point. They'll all cross a single point. So this line crossing corresponds to strong negative correlation, strong negative association. Okay. So if you're interested in the math, there's a lot of papers on the math behind it. It's been a long pursuit of some people in exploring the duality between orthogonal spaces and parallel spaces. The math is quite cute. The benefit that you gain by laying out the axes in parallel is that you can now plot a lot more variables. So scatterplot matrices have a sort of a limit of 5 or 6 variables, and then you can't really see too much. With a parallel coordinate, you can plot 20 variables quite easily. So that's one of the advantages. A second thing is it still is. So still primarily we're looking at pairwise relationships, because the axes that are next to each other, we can see more things. Right? And so if you change the order of the axes, you may see different features. And so that's important. So if you've probably heard when you're using histograms of your data, you should never just stick with one bandwidth, one bin width. You should always change the bin width of a histogram. With a parallel coordinate plot, you should always change the order of the axes a few different times, because you might see some different features. So ordering of the axes is important. All right, here's one for real. Okay, so here's a parallel coordinate plot of 1, 2, 3, 4, 5, 6, 7, 8 variables. So I've got 8 parallel axes. Each line here corresponds to a single row of my data, single observation. Each axis, the axis has been scaled by mean and standard deviation, so the variable has been scaled or standardized to have mean 0 and standard deviation 1. And so you'll see this vertical axis is centered at 0, and that shouldn't go much out beyond 3 and minus 3 for normal data. So what we can see, there's a lot of things we can see in this picture. There's some outliers. There's some clustering. I'll come back to that. There's some negative association. There's some positive association. And there's some discreteness. So these particular variables have got some sort of just separate values. So it's distinct values. This was produced with the GG Parkward function in the GALI package. All right, so how is it produced? We'll come back to some more examples in a moment. So how do you produce the parallel coordinate plot? Here's our data. So I've got 4 variables in this data. So x1, x2, x3, x4. I have 7 cases, so 7 observations, 7 rows. I first take that and I scale it. If I'm using standardizing scale, so mean and standard deviation, it just means that each column gets standardized. So this is my new data where I've got standardized values. They're all centered at 0 with standard deviation equal to 1, right? And that's what I plot. Right, and so then you draw it. So I've got my scale data, and then I draw it. Here are my axes, x1, x2, x3, x4. And I think I've got some of these labeled. Right, so that first row, minus 0.6, minus 1, minus 1, 0.1, corresponds to this line. So this is minus 0.6, minus 1, minus 1, minus 0.11. Okay. These are heavily rounded. That's the second one. So minus 0.2, minus 0.1, minus 1.2, minus 0.36. Okay. All right, so let's look at some standard patterns. So this is simulated data. So I just generated some data with particular features. And this data is essentially generated from a multivariate normal, but I shifted the means so that I've got 6 different clumps or clusters. So there's 6 very well separated clusters. So on each axis, I just centered the mean. On variable 1, I've got a group of points that have got a much larger mean than everything else. On variable 2, I have a group of points that have got larger mean than everything else. And that's what is creating this sort of up-down pattern. So on variable 1, most of my observations are here, and then I've got a cluster of points there. Right? And that cluster of points comes back to be the same as all the rest of them in the second variable. But I've got another cluster of points that starts off low and has got high values on the second variable. Okay, so this up-down pattern is saying I've got clusters. How do I work out that I've got 6 clusters? It's a little bit tougher. What you'd have to do is trace them through. And when you've got a lot of data, that tracing them through is harder, right? So that's primarily why pairwise we can see things easier. To see the multivariate structure, you need to be able to trace the lines all the way through. And so yeah, I think it's very hard to see that this clump only is up here and then it comes down and stays the same with the rest. We need some other tools to help with those ones. So primarily we can see that there are clusters. Working out that there are actually 6 clusters is a little bit more difficult. All right, same thing, only the clusters are not as well separated. So the previous one had very big separations between the clusters. These is the same, but there's some overlap between them. But I think you can still see some of the up-downs, right? So you can see a group of lines that starts up high and comes down, whereas a lot of other ones are fairly flat. And then there's another group of lines that go up there. Okay, so that same pattern, but not as strong as in the previous one. Okay, here's an example where I've got some outliers. Okay, these are extreme outliers in variables 1 to 3. So they'd be huge, huge outliers in the space. And you'd pick them up just by plotting one variable at a time. Primarily, we'd still be looking for outliers that you didn't detect from the low-dimensional plots. These ones you would detect with with just single variable plots. But this way we can see that there are outliers in 3 of the variables. Right? So lines that are on the extremes just are features of this they are outliers. This is what regular data would look like. So this is simply a sample from a 6-dimensional random multivariate normal, where the variables have a moderate amount of correlation between them. I think I put about 0.5 positive correlation between all pairs of variables. And so it's just a bit of a mess, right? So a little bit of up and down, but that's the sort of pattern where there's nothing particularly interesting. This is a very regular data set. Okay. Okay, this is the same type of data, but I've increased the correlation. So the correlation now is at 0.9 between every pair of variables, and so you can see it's flatter. So we didn't see as much as the crossing before. Right, so a lot more crossing with less correlation. Stronger correlation, positive correlation, they're much flatter. This one, there's a strong negative correlation between variable 1 and variable 2, and then 2 and 3. Okay. So that really is a bit distracting because having all the lines crossing is, that just is too strong a structure. If we take x2 and flip x2, then we'll get something that's a little bit easier to digest. So when you see a lot of strong negative correlation, flipping the axis might actually help digest. Right, so if I just flip variable 2, then I get back to this, right? All right, back to the first example of real data. Now let's pull out some of the pieces. So these are the outliers. So these little pieces correspond to that I've got outliers in the data. So there's a lot of points here, not just singleton outliers. There's a couple of outliers up there and a couple of ones up here. So most of these we're seeing on a single variable, but being able to trace them through, we might see multivariate outliers, but primarily we can see the single variable outliers there. Okay, some positive, clustering. Yeah. So clustering, because you've got sort of a empty area, we've got some clustering here. There's clearly clustering in these 3 variables and clustering over here, and in the last variable as well, there's some clustering. Okay. Strong positive correlation. We've got the flat profiles. And then some strong negative correlation. And then the discreteness. Right. Okay, so real data tends to have a combination of those features that we saw before. Next issue, scaling. So how you scale these changes what you can see. So we use the mean and standard deviation to scale. So this is what we've been using. This is probably more common if you use a parallel coordinate plot. Most people will use a min-max scale. And so on each axis will be scaled to 0 to 1. Right, subtract the min and divide by the range. It's the same data. Okay, it's the same data. It's just the variables have been scaled differently. So you emphasize different features according to the way you scale the data you're putting into it. So using the mean and standard deviation, I think we focus more on the correlation. Using min-max, we're focusing more on the univariate distributions and the extreme differences in the distribution. So the fact that we're going from fairly, I don't know, left skewed to right skewed. Let's use that one. And this last one, this is using a global scale. So I calculate the min and max across all the variables, and I scale each variable according to that global mean, min and max, or global mean and standard deviation. And you can see that for this data that makes no sense whatsoever. So global scale means I take the min and max of every variable, of all the variables. So use a global min and max. And so that's only really appropriate for very special cases. So if you're doing repeated measurements where you're taking the same individuals and measuring them multiple times, then it would be appropriate to use a global scale because you've got the same information and you want to take into account the temporal difference from one measurement to the next. If you're working with gene expression data or some of the bioinformatics data, they're all supposed to be measured on the same scale, and so you would use a global scale. Right? But for this data, you see it's quite extreme. Some variables have a range of like 40 to 70, and some are close to 0. So this left scale is the global min and global max. Yeah. Okay. So whatever scaling you can use it individually or you can use on a global scale. And there's a whole bunch of other different ways that we can scale. These are just examples. But I think that's generally an issue in statistics too, how you transform your data, how you scale your data. That's applicable to parallel coordinate plots too. Okay, so let's take a look at the Mexico City data. This is all of the variables. And so this first axis is the deaths, average temperature. I actually also have min and max temperature. Those aren't included here. Humidity, wind, NO, NO2, NOx, ozone, carbon monoxide, sulfates, and then particulate matter. So there's different sizes of particulate matter. So I've got one health variable. I've got, 3 weather variables, and then the rest are pollution variables. Okay, so the data's taken from these sites and then put together, and it was compiled by Hadley. So what are some of the things that you see in this data now that you're experts at reading parallel coordinate plots? What can you see? Say that again?
The last two has...
These two are almost the same. So if you know PM10, you pretty much know PM25. So strong positive correlation. You probably don't need both particulate matter variables. They both have pretty much the same information. What else can you see?
Outliers.
Some outliers, particularly in the sulfates and the carbon monoxide. The fact that they go up on the sulfite and then come down means it's probably just that variable. So it's not across multiple variables. Although you see a few coupled here, there's one day that had an extremely high amount of the nitrogen pollutant. There are also some days that have very low values of those. Okay, what else?
Negative correlation between deaths and temper.
Yeah, so negative. negative correlation between deaths and average temperature. And then temperature and humidity. Yeah. I don't know much about weather in Mexico City, but yeah, the lower temperatures seem to be associated with the higher humidity. Okay, what else? Yeah, it looks like a little bit of clustering, particularly here. Yeah, maybe over here too. And a little bit sort of wherever you see these slightly less dense means there's a bit of a gap. And so you can see sort of these in a few places, just here. Maybe even in the ozone and the carbon monoxide, you see a little bit of clustering there too. Okay, I think that's, you've got it all pretty much. All right, yeah, question?
Well, you plot, I don't know if you understand well the graph, but you plot the weather variables together and the pollutant variables together. So what I'm seeing is something that I know that will happen.
Mm-hmm.
I know that the higher the temperature, the less the humidity. And it doesn't tell me anything about the relationship with depths. And
right.
And so I wonder if I can shuffle.
Yeah, exactly. So you might want to shift deaths in the order. Yeah, and absolutely. That's so. Yeah, I didn't do that here, but we should be switching the order to place different emphasis or look at different things here. Yeah, absolutely. You might want to particularly look at it in relation to some of the pollution variables as well. Yeah. Okay. So yeah, we pulled out all of these pieces from the plot. There may be a little bit more in terms of some of the univariate distributions are slightly skewed, and so we may want to be transforming those. And in terms of interpreting some of the results, like higher deaths if the temperature's lower, that surprises me a little. And the lower temperature, higher humidity, I don't know, that surprises me some because I always associate higher humidity with higher temperatures, but I don't know. And then there's a few days that were high pollution. Because the wind is close to the nitrogen variables, you can kind of see that the lower the wind, the slightly higher values of those ones.
Excuse me.
Yeah.
I have a question. I understand that this is a big. You can see 10 different tendencies with different variables. But my question is possible to obtain a math modeling, a math equation that I can prognosticate the.
Yeah, exactly. So this is just sort of pre-screening your data, right? So in general, this is supposed to help you build a better model. And this is not making any final conclusions, but it's just going to help us make sense of the model, maybe help choose the appropriate model, help decide whether the model is fitting correctly or whether it's missing the extremes. Like so, yeah, but it's not to substitute for the modeling. It's just supposed to help that. Yeah.
Is there any criteria of sample size to be appreciated adequately tendency of the data?
So how much the sample size?
Approximately 100.
No. I mean, the biggest problem with parallel coordinate plots is the larger the sample size, the denser it gets, and the less you can see. So it's reasonably good for small sample sizes. with larger sample sizes, you need some additional tools to help understand what are the main patterns in it. Yeah. So we're really not saying too much about sample size here. Yeah. Yeah.
Is there any option in the package that you can select a subset of data, such as you can follow all the trajectory in a graph? For instance,
right.
in a cluster, you can follow all the trajectory?
Yeah, if you use the ggalley package and the ggparkward, there's a lot of different ordering functions that you can use. So some of, you can, well, primarily those ordering routines are based on if I've got groups in the data, like if I have a class variable, it'll try to put the variables that have got a difference on those classes close together. Separately, you might calculate correlation and pass that order in. So if I've got my strongly positively correlated variables, put them together. Then there's another set of functions called scagnostics. Has anyone heard of scagnostics before? The scagnostics has been around since the 1970s. It's one of the John Tukey's inventions. So it's a play on diagnostics, but it's diagnostics for scatter plots. And so for pairs of variables, you fit a graph to the scatter cloud, like a minimal spanning tree, for example, and then use that to calculate all sorts of statistics. And the statistics, they're called are skinny and clumped. They have great names. I mean, Tukey was fun with great names, but there's a package in R that will calculate scagnostics, and the parkwards function here will use those criterion to order the variables. So you can say put all the clumped variables together. So order the variables according to the clumpiness of them. So the ordering, so using some of those, you could think of these as models, but it's not models. It's just exploratory data analysis. You calculate all these different criteria on your data and then use that information to help you sort through the information, sort through the patterns.